All right, welcome to The Explainer. Today we're taking a seriously fascinating journey into the actual mechanics of how we learn, understand, and truly master numbers. We're diving deep into Chapter 13 of our source material. It's playfully titled The Transport Museum, but hey, don't let that whimsical title fool you. Our whole goal today is to enthusiastically break down exactly how modern math education builds this deep, almost intuitive number sense. We are stepping way away from that rote, mechanical math of the past, and we're going to explore how structural visual aids and just some simple logical steps can literally empower anyone to grasp complex calculations with absolute confidence.
But before we get into the nuts and bolts of the chapter, I actually want to start with a direct challenge to you. How would you solve 15 multiplied by 14 in your head right now? Really, be honest with yourself. Does your brain just immediately freeze up? Do you instinctively reach for your phone or a calculator to do the heavy lifting? Because for a lot of us, double-digit multiplication is the exact moment math just became intimidating. But what if I told you that by just kind of shifting your perspective a bit, a problem exactly like this becomes something you can mentally solve in seconds? No calculator needed.
Okay, let's dive right into this and look at the learning journey we're taking today. We're going to start by moving beyond rote memorization. Then we'll uncover the sheer power of splitting numbers. After that, we'll scale things up with tens, see it all come together in the brilliant box method, and finally we'll ground all of this in reality with real-world remainders.
So, Part 1. Beyond rote memorization, building flexible numerical fluency.
You see, the core philosophy of this chapter is that math is a real intellectual journey. It's not just some dry list of problems you drill into your brain until you memorize them. To really bring this to life, our source material introduces us to students like Amala, Rahi, and Farzan. As they visit the Transport Museum, they aren't just handed worksheets with equations. Instead, they're looking at actual physical objects, we're talking arrangements of wheels, groups of pebbles, and they are discovering the visual math patterns hiding right there within them. Helping students visually recognize these patterns, that teaches them the why behind the numbers, rather than just the what. It's all about seeing the math living and breathing in the real world.
Section 2. The power of splitting, breaking down intimidating numbers. Now, what's really interesting about this slide is how it introduces the foundational strategy of the whole chapter.
This strategy right here is splitting, and it is an absolute game changer. Suddenly, that intimidating 15 times 14 problem from earlier, it totally loses all its power to confuse us. Why? Because splitting teaches us that no number is this big, scary monolith. Actually, every large number is really just a combination of smaller, much friendlier numbers waiting to be unpacked. So, step 1, we take our scary problem, 15 times 14. Step 2, we split that 15 into much friendlier, super approachable numbers, which are 10 and 5. Then, step 3, we just multiply both of those friendly numbers by 14. We all know 10 times 14 is 140, and we know 5 is just half of 10, so 5 times 14 has to be half of 140, which is 70. Add 140 and 70 together, and boom, you have 210. By just splitting the problem up, complex mental math turns into a totally logical, easy sequence.
Section 3. Scaling up with tens, finding the pattern to multiply larger groups. Let's move to Nez and Z and see how this builds on what we just did.
Because once you understand those basic mechanics of splitting, you're going to need a way to scale that logic up to handle even bigger challenges, right? And this is exactly where the curriculum introduces the sheer magic of scaling with multiples of 10. The textbook intentionally places these equations right side by side to trigger pattern recognition. Look at it. 14 times 10 is 140. 14 times 100 is 1400. It seems incredibly basic, I know, but visually comparing these teaches students that understanding the behavior of tens instantly and easily scales to understanding hundreds. You're not learning some entirely new complicated rule for bigger numbers. You're literally just applying the exact same pattern on a larger canvas.
To really make this stick, the source introduces a very specific definition, which they call the language of tens. So, instead of looking at 12 times 20 and seeing two separate two-digit numbers crashing into each other, students are taught to just think of 20 as two tens. So, 12 times 20 simply becomes 12 times two tens. While 12 times 2 is 24, so you have 24 tens, which gives you 240. This specific kind of language is an absolutely crucial psychological tool. It strips away all that anxiety and allows students to conquer much bigger multiples without breaking a sweat.
Which brings us to Section 4, the real climax of this whole scaling logic, the box method, conquering massive multiplication.
Okay, so we've learned splitting and we've learned the language of tens. Now we arrive at the point where these strategies actually combine to solve truly massive mathematical problems.
Just imagine a student, or honestly even an adult, being asked to tackle this calculation out of nowhere. 64 multiplied by 152. I mean, without a calculator, that looks like an absolute towering wall of numbers. But I really want to reiterate the core message of this explainer here. With the right structure, this is actually incredibly simple. We just need to apply the splitting and scaling tools we've already mastered.
And this brilliantly illustrates exactly how it's done. The box method takes 64 and splits it right down the side into 60 and 4. Then it takes 152 and splits it across the top into 100, 50, and 2. Suddenly, you aren't doing 64 times 152 anymore. You are doing 6 very easy, totally bite-sized multiplication problems using that language of tens we just talked about. 60 times 100 is 6,000. 60 times 50 is 3,000. 60 times 2 is 120. You literally just fill in the boxes, add up the clean round numbers, and you get 9,728. It takes this nightmare equation and turns it into a totally satisfying puzzle.
Finally, Section 5, Real-World Remainders, Applying Division at the Transport Museum.
All right, let's shift gears entirely away from multiplication and get into division. To ground this math in reality, the chapter sets up a really fun scene. This is the toy train our student Rahi spots at the museum. The problem she's facing is highly practical. Rahi needs to fit 324 school children into this train, and she figures out that each coach seats exactly 14 children. So how many coaches do they need? This isn't just abstract division on a whiteboard, it's literal event planning.
And the way the textbook handles this division is honestly just brilliant, because it's so practical. Instead of diving straight into some confusing, abstract long division algorithm, it uses repeated subtraction of chunks of children. Think about it. You have 324 total children, and the coach capacity is 14. So let's just subtract 10 coaches all at once. That's 140 kids seated right there. You track the remaining children, and then you just subtract another 10 coaches. This highly visual chunking method makes the abstract concept of division feel exactly like what it is, like you're actually loading kids onto a train step by logical step.
But as they go through this whole process, seating kids 14 at a time, calculating the exact number of coaches needed, they hit a wall. They reach the very end of their calculation, and they are left with this number right here, 2. There are exactly 2 children left over who haven't been seated yet.
And this leads to a fantastic, almost philosophical real-world question posed directly by the book. What do we do with the remaining 2 children? Look, in a purely abstract math worksheet, a student might just write down an answer like 23 remainder 2 and just walk away. But in the real world, math is about logical problem solving. You literally can't just leave 2 children standing alone on the platform at the museum. This brilliant scenario forces the learner to interpret what the math actually means in physical space.
The chapter defines this concept very clearly. Such remaining number in a division problem is called remainder. So the crucial point is that by teaching it through the lens of these train coaches, these methods ensure that kids tie this abstract term back to concrete reality. A remainder isn't just some leftover digit floating on a page. It represents real kids, real objects, or real limitations in the physical world that require a highly practical solution, like, in this case, realizing you need to order 1 extra coach for the train.
We've seen how splitting, scaling, the box method, and real-world chunking completely and utterly demystify complex math. So I'm going to leave you with this final thought and a bit of a challenge. How will you apply these foundational building blocks of numerical fluency in your daily life? The next time you face a massive number, I challenge you to just stop reaching for the calculator. Visualize the patterns, split those numbers into friendly pieces, use the language of tens, and just trust the structured process. Thank you so much for joining me for this explainer, and definitely keep exploring the hidden patterns around you.